Okay, for the next segment, we're going to talk about concurrency and performance. So I mentioned that in Lingua Franca that the reactions of a given reactor are mutually exclusive, you can't have two reactions within the same reactor executing at the same time. But if you have multiple reactors, the reactions within distinct reactors can certainly execute at the same time, and that's often very desirable, in fact. So we're going to start by reintroducing Christian Menard, who's again working with Professor Jerónimo Castrillón at the Technical University of Dresden. And Christian invented for Lingua Franca a very clever syntax for expressing very compactly fairly large programs with a lot of concurrency in them. And so, Christian, I'd like to turn it over to you to show that off.
Yeah, hello again. So I will start again with a simple example, and it looks again similar to what I've shown earlier. So it's three reactors. We have our counter, we have a printer, and an adder this time in the middle. So we want to perform some computation. Very simple in this case. We just receive a value from the counter, and if we increment it, by default, it's incrementing by 1. And I can just quickly run this to show you what it does. Single adder, and it's basically showing the same output as we've seen earlier for the pure counter. It just increments everything by 1. Now, let's mention we want to solve a slightly more complex problem that has some concurrency in it. So let's say we want to add 2 values, and the addition should happen concurrently. The very simple thing I can do is just instantiate second adder. Let's name it A1 and A2, and let's maybe say this one it's to the input. Now the diagram updated, and I have 2 reactor instances. I need to fix my connections now. This is also shown by these error markers here. So I renamed or added new instances. So I have to adjust those here, and I actually also need to duplicate this connection in order to connect both of my instances. Right, and now the output of the counter, it's sent to both adders, and I add a different value. And since this is in different reactors and they're independent on each other, this can actually is concurrent, and it can actually be executed in parallel to each other. And finally, I also need to fix this connection to the printer. And in the naive thing I could try is actually to connect both outputs of the 2 adders to the same input port of the printer. However, Lingua Franca doesn't allow us to do that. If it would be allowed, this would be a potential source of non-determinism, because it isn't always clear in which order these messages should be processed, and merging is quite hard. So this is forbidden in Lingua Franca, and in order to resolve that, what we need to do is actually also introduce more ports on the printer. So we can just duplicate that port, have a reaction to both of the ports, and then I can also duplicate this so that both values are printed. And now I can fix my connections here. So if I were to run this, I would get the output from both adders, and both lines would be printed with slightly different values. Now, I guess you can imagine that this is quite tedious to do by hand for very large programs where you maybe want to have 10 adders or 100, or maybe have a very complex structure. So there's a neat shortcut for this. So instead of just creating multiple instances by hand, what you can do is create what we call a bank of reactors. So it's multiple instances which show up stacked in the diagram view. So it behaves like an array of reactors. And actually, let me make it slightly more complicated. So I'm going to introduce a parameter here, and I can parameterize the width or the size of this bank. And now we need to fix connections again, so let's reverse that change to connect the header back. The IDE actually at this point shows a warning. So it tells me the left width is 1, but the right width is 4, and it doesn't work. So what it tries to do is just, we have a single output port here, and it connects them to the first output port. It connects it to the first output port on the right side. And so it creates a single connection. In order to actually create 4 connections and to broadcast the value, what I can do is add this little plus here, which means broadcast, and then the output is replicated and forwarded to all the different instances of the header. And for the printer, I can do something very similar. So again, I'm just going to copy this. Let's introduce this parameter and also forward that to the printer. And now I can create a multiport. That's how we call it, basically an array of ports. And we have n ports here. I need to fix up this direction a little bit. So it directs to in. And now since we have an array or a vector in a C++ target of ports, what we can do is we can iterate over it. So let's create a for loop. This, and we can remove that, and we can adjust the output maybe a little bit. So this can print from which index it comes, and then it prints the value from the specific port. And so we iterate over the indices, and then we can access these individual ports. And then the last thing I need to do is fix the connection down here. So this creates a multi-port connection where the 4 instances of the header port, their outputs, are connected to this multi-port input, which is actually shown by this little changed triangle here that it's multi-port. I think I can also add the width here. And one final thing, change I want to make. So in order for all these headers to receive a different value, what I can do is just rename that to bank index, and that will be automatically assigned on instantiation, and each of the headers will get a different index. I can use it here. Now, if I run this, I will get output, of course, from the 4 different headers. Yeah, so it's printing this, and of course the first one, the index 0 adds 0, and so on. So the last one adds 3. And what I now can also do is I can play around with this parameter that we gave, this n. So I can say, let's do this for 10 headers, or let's do this for 1,000 headers, and this automatically adjusts the structure of the program and instantiates vectors accordingly. And with this quite simple syntax, it actually allows you to build quite complex patterns and solve various kinds of problems in a neat way. And that's it from my side.
Okay. Thank you, Christian. So next, I would like to reintroduce Martin Lostra, a postdoc at Berkeley, who's going to show us how these kinds of programs execute in parallel on a multi-core machine. Martin, take it away.
Thank you, Edward. Let me share my screen. Okay, so this is also something that you can follow along with. This is the same mechanism that we used before. You start a new Lingua Franca project. Let us call it parallel, and then select the parallel project template. So this example is in the same vein as the example that Christian just discussed, and the key here is to show that we get speed up from using multiple threads or workers. So the runtime is constructed such that the lack of data dependencies between reactions. So first of all, they have to be in separate reactors, and second, there has to be no data dependency between them. They are executed concurrently, and if the runtime allocates more than one worker, which it is capable of doing, if you use the threaded runtime in C, for instance, C++ uses a very similar mechanism, and that will allow reactions that are triggered at the same logical time instant to execute in parallel. And that, of course, yields a speed up. So this simple program here, the work is symbolized by this take time reactor, which really just sleeps for an amount of time. And it has a source that produces inputs that are taken by the take time reactor. As Christian explained, these are allocated in a bank, so there's 4 of them, and this gets plugged into the destination. So when we run this, I think it has already compiled. So let's cd into parallel. We get what we would expect. So the source produces events with a spacing of 200 milliseconds between them. And also there's a timeout of 2 seconds. So the program stops executing. Currently, this parameter here, this target property, denotes that it uses only 1 thread. So even though the dependency graph here clearly indicates that these take time reactors are in parallel, they have no dependencies between them, they don't share any state, they can be executed in parallel, there are no resources to do so. But if we provide those resources by saying, well, now take 4 threads instead of just 1, the program in the meantime recompiles. So you can look here at the elapsed physical time. So the logical time that elapsed is only 2 seconds, as we specified here in the target property. But the physical time that elapsed is significantly longer, and that is because there is not enough capacity of doing things in parallel. But if we add capacity, then we can get a lot closer to that goal of our 2 seconds. And you see, we're still a little bit late, but only by 200 milliseconds versus, a factor. So this is a very simple demonstration of exploiting parallelism. There are also other ways of doing that. Let me show another example. So let's open another project. I call this pipeline. There's a pipeline template here, and this demonstrates pipeline parallelism that is using the exact same mechanism that we discussed so far, exploits parallelism automatically. However, there are some caveats. So let's go into that. So here we have a pipeline Again, this is not about the functionality of the program. These are actually adapted examples from regression tests that we run automatically when changes are pushed to our repository. So these are kind of constructed simple examples that test particular things. But it's a good illustration of how we exploit parallelism. So here's a pipeline, and using the syntax from Christian, we have here this this pipeline construction where we have one reactor that feeds into a bank that is daisy chained. So you could essentially unfold this first time reactor, plug it after another, then plug it after another, and then plug it after another. This is just a really compact, nice notation that signifies the same thing. Now, we allocated 4 threads like we did with the previous example, and let's run it. So let's go back up into here. So let's run this example. And the issue here is very similar. We're lagging behind logical time. So we specify it to send messages with a period of 100 milliseconds, but we're unable to keep up because we don't exploit any parallelism. But why is that? Because we allocated 4 threads. Well, it is a pipeline, and you have to, so at the first logical time in a pipeline, the first functional unit, which is our first time, take time reactor, has some work to do. And then if you construct a pipeline properly, then at the second tick, the first one and the second one have something to do, and so forth. But then that only works if if it's clocked. And so the problem here is that the functional units have no delay between them, and the delay has to match the period of the send count reactor. So here it matches. We're using 100 milliseconds. And when we fix that, and you can see here along all the edges, we introduce a delay, we immediately see a speed up. So this kind of really concisely shows how we make use of Multicore. Yeah, that was it. Back to Edward.
Thank you, Martin. So one of the things that we have been doing is assessing performance of Lingua Franca, and sometimes, as anyone who has experience debugging parallel code, it can be quite difficult. And so we've put some effort into building some tracing mechanisms that are by design designed to be very low overhead. So I would like to introduce another recent addition to the project. This is Professor Håkan Kim, who is an assistant professor at Hanyang University in Seoul. Håkan was previously at Google just until August, and before that was a PhD student in my group. And so we know Håkan very well and have worked with him in the past. And Håkan will show us around the tracing mechanisms that currently exist in Lingua Franca. Take it away, Håkan.
Thank you, Edward, for the kind introduction. So I'll be presenting tracing mechanisms in Lingua Franca. In general, tracing is useful for recording and analyzing information gathered during the program execution, for example, for performance analysis, as Edward just mentioned. LF supports tracing tailored to reactor models. More importantly, LF minimizes tracing overhead by recording the information in a compact binary format. The events recorded in traces include calls to schedule events, beginning and end of reactions, worker thread related events, and user defined events. The timing of each event is also recorded, including physical and logical time, microsteps, and delays. If there are triggers for these events, those triggers will be recorded as well. And the full list of trace events can be found in trace.h file. Currently, tracing is supported in C, Python, and C++ targets. The C++ target requires Linux and third-party libraries, while C and Python do not require any third-party libraries. And you can find more information on the wiki. Okay, now let me begin the tracing demo. To enable tracing in a Lingua Franca program, you can simply add a target parameter called tracing and set it true. This tracing.lf program consists of a source reactor, destination reactor, and 4 reactors running concurrently using banks and multiports that Christian showed earlier. And if you run this tracing-enabled LF program like this, tracing.lft file will be created. This .lft file is a binary file, so we can convert it to human-readable formats using utilities provided by LF. One utility is trace to CSV. When we run this, it converts .lft file into 2 CSV files, one for the row trace events and the other for a summary of events. Another utility is trace to Chrome. And if you run this, it converts .lft file into .json file that can be loaded into a visualization tool called Google Trace Viewer. And if you have a Chrome browser, you can run the Trace Viewer by simply typing Chrome://tracing in the address bar. And then you can load .json file that we just created and see the concurrent events in different colors. For example, you can see the tasks, the concurrent tasks, and worker rate events as shown here. In addition to these events, you can also view the user-defined events, this number of destination invocations, which are registered and recorded in the LF program. And if you open CSV files like this, you can see the row events as shown here, or also the summary as shown here. And you can enable tracing in Python as well. Yeah, let me just show you how so that this works. Example. As you can see, the .lft file is generated. Okay, that was about it for tracing in Lingua Franca. And thank you, and back to Edward.
Thank you, Håkan. I would like to next reintroduce Christian Menard from TU Dresden. So Christian has been leading an effort that has actually involved several people to do some serious performance benchmarking in Lingua Franca to learn about the consequences of our choices in language design. And so Christian, if you can tell us where we're at currently with this these performance measurements, that I would be grateful. Thank you. Take it away.
Of course. So, as Edward said, we of course are also interested in understanding how well Lingua Franca performs compared to other solutions that are out there and that are used in various projects. And of course, then the first question is what to compare to. And we decided to compare against some of the actor frameworks that are out there. Because actors are quite related to reactors, in a way reactors can be seen as an extension of the actor model. And we also found a benchmark suite that covers various problems and implements them in various actor frameworks in order to provide a way to compare them. Particularly interesting for us was Akka, which is Scala-based and very popular in the JVM world, and the C++ actor framework, which is very popular in the C++ world, and also quite competitive in performance. And so, as I said, we found this Serena benchmark suite, and we tried to port this to Lingua Franca. I said we tried because porting these actor benchmarks or actor programs isn't always straightforward, because the semantics of Lingua Franca and reactors are very, very different from the ones of actors. In actors, everything is asynchronous. In Lingua Franca, everything is synchronous by default. But we tried our best to capture the structure and of the programs and their behavior in order to allow a fair comparison. And what is seen here in this, what you see here in this plot is the results of a recent measurement I made. That's run on a 20-thread machine, and comparing the performance of Lingua Franca, the C++ runtime, the C++ active framework in green, and Akka in red. And actually, this graph is normalized to Akka, so Akka always has performance 1, and then if it goes up, it's worse, and if it goes down, it's faster. And what we can see is that I would say we are at par with both CAF and Akka. And some of the benchmarks, we are somewhat slower, quite a bit even here for those big ones, it goes way up. But for others, we are also really, really fast, like the cigarette smokers here. It's more than factor 10 faster than the Akka version. We are currently still investigating as to what the reasons are, and we believe we can actually pull down a few of these bars quite a bit. But for some benchmarks, the reason is also this mentioned difference between the semantics of reactors and actors. For instance, I believe this bank transaction here is lower because things are not handled asynchronously, and we probably can't do much about it. But on the other hand, there are some problems like the cigarette smoker problem here, which is a concurrency problem that can be solved much more elegantly and more performant in Lingua Franca. I would also like you to show 2 different plots just to give you an idea of how Lingua Franca programs can scale. So this is kind of zoomed in on 2 of the benchmarks. This ping pong benchmark, really simple benchmark, just 2 reactors, one says ping, the other says pong back, and then they go back and forth. And as you can see, the performance is quite stable if you add more threads. It drops down a little bit, but not too bad. Same for the C++ actor framework, although it's like factor 2 slower. And actually in Akka, if you add more threads, then you add more overhead and you lose performance actually. Reason being, of course, that there is no concurrency and no exploitable parallelism in the program. Another benchmark that has concurrency and exploitable parallelism is the all pairs choice path benchmark. And here you can actually also see that Lingua Franca scales really well. So you add more threads, you gain performance. Same actually also for Akka, but it kind of stops at 4 threads and then stabilizing. And for the C++ active framework, it's also scaling, but then at some point it's going back up again. So it's kind of doing a weird curve. And interestingly, actually, Lingua Franca single-threaded performs worse in this benchmark than Akka, but if you scale it up, then it's better. So yeah, that's just to give you a brief overview of what's happening in this regard and where we're standing. But this is still a work in progress.
Great, thank you, Christian. So the last topic in the concurrency and performance section is a very exciting one to me, which is federated execution. So what you've seen so far is mostly Lingua Franca programs running on multi-core machines. But largely due to a tremendous amount of work by Sarush Bateni of UT Dallas, we can map Lingua Franca programs to multiple hosts and synthesize the communication between them across the network automatically. So I think mostly it's been Sarush. I've had some hand in developing this, and Martin Lostra also has had a significant hand in developing this, but Sarush is going to give us a brief introduction to this, what we call federated execution of Lingua Franca programs. So take it away, Sarush.
Thank you, Edward, for the kind introduction. So just to give an overview of what we're going to show here is first, I'm going to show you how we can create a distributed LF program. Then I'll show you how to execute each distributed node and how to deploy. And then I'll briefly talk about how distributed LF programs are coordinated. I'll talk about two coordination strategies, one conservative and one decentralized, which is much less conservative. For this demo, for the purposes of this demo, I will use a hello world, which is slightly modified. You can find this hello world example on our repo under the distributed hello world example in the examples directory. So feel free to try these. Our federated infrastructure is only supported on Linux and Mac OS. We have plans to support Windows in the future. Okay, so with that, I am just going to jump right into it. Okay, so just to briefly explain how this hello world example is modified. So we're still using two reactors, just like the other hello worlds that you saw in Python, C++, and so on. However, because we want to demonstrate that we have message passing infrastructure implemented in Lingua Franca, what happens in this example is actually that the message generator, the source, will produce a string, which is consisted of a prefix and a number, and it will send that message to this print message reactor, which will in turn print that message. The other thing that we augmented this example with is we also utilize this Lingua Franca API, which is getCurrentTag, which returns the current logical tag or logical time of the application. And the idea is that we want to check that indeed the semantics of Lingua Franca are honored even in a distributed setting. Okay, so I have here an unfederated program. So it's just a simple hello world with a main reactor. And so I would need to get rid of the bin directory and the source directory. Apologies for that. Okay, so now I'm gonna, as always, save this program, this hello world program. And what I'm gonna do is now look in the bin directory. Whoops. I am in the wrong directory. Examples. Okay. So now I'm in the examples directory. Okay, so if I look, I would need to remove the folder again. Okay, so I'm going to recompile the program again. And if I look in the bin directory, what I will see is when I save this program, the Lingua Franca infrastructure compiled it and produced a binary for me, a hello world. So this binary contains both of these reactors. And the way that they communicate is quite easy. They actually just pass a pointer. So this message being sent from the message generator to this print message is just as simple as passing a pointer. So let me now execute this single application to see what it does. So the other thing this program is doing, as I said earlier, is also printing the logical tag at which things are happening. So if you look at these first two lines, you can see the message generator is producing a message at 1 second, and that is because it is driven by a timer with an offset of 1 second. And you can see that the receiver receives that message also at 1 second. Okay, and that is inherently the semantics of lingua franca, right? Which is that this execution of reactions is synchronous. Okay, so now the way I can make this program into a distributed version is very simple. So let me clear this. All I need to do is I change this main reactor to federated. And now if I look at the bin directory, now I can see here, you can see in this terminal that we no longer just have one hello world. Now we have 3. And we still have this hello world here, and I'll talk about that in a second. However, you can see that 2 new things appeared. So one of them is called hello world underscore print, and the other one is called hello world underscore source. And these names come from the instantiations of these reactors in the federated reactor. So you can see here that I have a source reactor, and you can see here that I have a print reactor. And the lingua franca generator automatically has created 2 separate processes for each of these reactors. Okay, so now you can take these processes and put them on different machines and execute them. However, to facilitate that kind of a workflow, we also produce a bash script. So if I look inside this hello world, you will see a rather sophisticated bash script, but really what it does is it will launch these 2 federates. And I can execute this by just running that bash script. Okay, and now you can see that you can see that essentially the way the program behaves is exactly the same as before. So you see that the source reactor is producing a message at 1 second, and the receiver will receive it also at 1 second. You might also note that now we have our messages augmented with these names. So we call our distributed nodes federates, and they're here indexed from 0. So federate 0 will be the message generator, and federate 1 will be the print message. You might also notice that the semantics of lingua franca are still preserved, even though we're running completely 2 different processes. And the way that it's preserved by default is using a coordination mechanism loosely based on high-level architecture, or HLA. And what will happen is that a third process that is not shown here will be created for this federation, called an RTI, runtime infrastructure, from HLA, which will be in charge of coordinating the semantics of lingua franca between these 2 reactors. However, that those of you who are familiar with HLA might realize that that's very conservative. First of all your messages will now have to go through that coordinator, through the RTI. Second of all, these 2 reactors need to be in constant communication with the RTI to be able to coordinate and correctly execute. We do have a less conservative central coordination mechanism, which you can use by using this target property. So you can set coordination to decentralized. And once you do that, we will still take care of the communication ourselves. So all you need to do is in your message generator, just like an ordinary lingua franca program, you just will set a value to a port, and we'll take care of transferring that message to its destination. However, we'll no longer take care of the coordination. Instead, you would need to use an alternative coordination mechanism, which the one that we're using is, in this example, is loosely based on Tides and Google Spanner, in which you make some assumptions about the network delay and clock synchronization error and execution times, and you define what's called an STP offset or save to process offset, which will offset the execution time, in this case, of this print message long enough so that it can receive messages from the message generator. Okay, so if I execute this, so hello world decentralized STP. So even though the RTI is no longer in the way, I can see that my source and destination are still honoring the semantics of lingua franca, meaning that the receiver is receiving the message at the exact same logical time as the source. However, if this STP offset wasn't large enough, so let me reduce it to 1 millisecond to cover the overhead involved with this communication. Did I do that correctly? I don't seem to be getting the warning, so let me. Maybe 1 second is still large enough. Yes, so let me just do it 1 microsecond, just to make sure. Yes, so 1 microsecond is obviously not enough to cover the overhead of communication and execution. So now you can see that we automatically have detected that the semantics of lingua franca was not honored. And you can do that in your lingua franca program by simply using this special syntax, which is an STP handler. And if you detect that the semantics of lingua franca in this case is broken, we'll invoke this STP handler, which will just print that this message is tardy. And it will tell you what the intended tag of the message was and what the tag is that it's trying to execute. And yes, so with that, back to Edward.
Thank you, Sarush. So you can imagine being able to use this for genuinely distributed applications, and that's one of our principal objectives.